4. I mean, we've got, I think, communications, there's a section at 4, but that's just for people who are gluttons. Right? Oh, it's time to begin. Okay, let's see if we can remember what we're doing. We have spent some time now on the Maxwell model. So we finished the generalized Newtonian model, and we've moved on to the next one, which is actually going to end up to be a group of constitutive equations that all tell us something about the time dependence of material behavior. It's also going to turn out that all constitutive equations are going to reduce to this equation in the linear viscoelastic limit. So whereas the generalized Newtonian fluid model was simple and appealing in that it just took off from the Newtonian model into non-Newtonian, this one's a little different, but it's going to be a fundamental type model. It's going to be one that the small amplitude in the linear regime is true for all materials. So it's really going to be very applicable. So what have we done? Let's see. I don't know that maybe I want to even start further back with my review. Let me get one more set of slides up here. What model am I talking about? I'm talking about, no, I don't want that one. I'm probably just, there we go. I'm talking about the Maxwell model. Now, where did we get that? We started by looking at this simple model where I started with the Newtonian case and added a term that referenced the deformation of the fluid a little time ago and had a function in the front that was decreasing. And we saw from playing with this model that we could get some amount of startup effect. So when we did the shear startup for this model, we saw it step up from 0 to something, mimicking slightly the type of behavior we know exists. So we were on to something that reference to deformation in the past could allow us to mimic time dependence. So we kept playing with the model, adding yet another term. We got a more gradual rise. And then we added a whole bunch of terms with exponentially decreasing coefficients, and skipping the details, we got to this model. So this is something I call the integral version of the Maxwell model. It has two parameters in it, a viscosity and a relaxation time. So this is the model we're studying, the basic version of the model we're studying this semester. I mean, this week. Now, we also looked at that from a different approach, which was from Maxwell's original approach, which was to start with a differential equation. And in fact, except in my book, I don't think there's anywhere else where they developed the model the way I did by adding it up in the sums. Most of the time when this is introduced in polymer studies, they start with this constitutive equation. And where does this come from? This comes from this picture of a spring and dashpot in series. And knowing that the spring acts like an elastic spring and the dashpot acts like a Newtonian liquid, we now need them to act in in series. So we add up the displacements of the spring and the dashpot, a little bit of algebra, and we get a force displacement equation that's very familiar in mechanical engineering. Between terms that involve the force, those come from the viscous terms. And a term that involves a derivative of the force, those come from the spring terms, and the derivative of the displacement. These lead to, if you just make an analogy between force and stress and displacement and rate of change of shape, and you get a shear version of the differential equation, which we then just spontaneously, and I'm going to show later that this is a bad idea, being this spontaneous, but nevertheless, this is what was done. Take this single component equation and say, let's just say it's true for all 9 components of the stress tensor. Seems reasonable. There's nothing obviously wrong with this. We're going to find out later that there's something a little bit wrong with this, at least when you have large deformations. So this is actually a hint I'm giving you now of why our solutions from here on are going to be limited to the small deformation regime. But for now, we're just going to make the guess that we can go from just tau 2,1 to all 9 of the taus. So we now have a new constitutive equation, this differential equation. And as we have done with the Newtonian model and the generalized Newtonian fluid, we're going to take it out for a spin and see what it predicts. Okay? We also showed, I did a little calculation at the end of class, at steady state this term goes away and you get the Newtonian case, and at large deformation this term is negligible and you get the elastic solid case. Okay, so here we are. Now we have a new constitutive equation. Let's check its predictions. We can predict anything we like. Steady shear, steady elongation, startup, step strain, small amplitude. We're actually going to do a few of these because they're important for this model. We're going to do, let's see, am I going to do steady shear? I might be doing steady shear. We're going to do, maybe in the homework, you might do startup for me. We're going to do step strain, and we're going to do small amplitude oscillatory shear. Okay, so let's start with steady shear. Let's go back and pick up the equation. Well, maybe I have it on the next slide. There it is. Here's our constitutive equation. Tau plus, these are just parameters of the model so far. Eta naught over g d tau dt equals minus eta naught gamma dot. This is the Maxwell model. And we want to make predictions of material functions based on this Maxwell model. So let's think, how do we normally do this? If we want to make a prediction of the viscosity, how do we do it for a constitutive equation? If it's the complexity of this equation that gives you trouble, tell me how to do it for Newtonian or generalized Newtonian. I'm asking if you have a constitutive equation, so let's say the Newtonian, how do I predict what a material function is given by for that equation? How would I predict viscosity and first normal stress coefficient for, let's say, the Newtonian case? Right. So we need gamma dot, right? So we build gamma dot is del V plus del V transpose. We know V. Every time we do a material function prediction, we always know V. It's always sitting here right at the top. So we know that. This is, we've seen this before. Sigma dot 0, sigma dot 0, 0, 0, 0. We put sigma dot for this flow, which is gamma dot naught. So that makes this a constant. We plug it in here, and then we go here. All right, so how do we do it for this equation? Do you see a problem? What's the problem? Right.
Differential equation is not.
Stress is there twice. It's a differential equation in stress. It's not. We can plug gamma dot in all we like, but it's not explicit. So actually, our first step is going to be before we even start on this problem, we're going to make it explicit in stress, and it's not that bad. It takes a few pages of calculus, but it's not that bad. This is a simple linear differential equation with constant coefficients. So let me start by calling this lambda. And we're going to solve this differential equation. Now, it's a tensor differential equation, but it's just 9 equations all written very compactly, and they all get solved the exact same way. So we just keep carrying the tensor notation along with us. Okay, so we just leave these taus and this gamma dot exactly like they are and carry them along. This particular differential equation, so if you go back to your differential equation class, you may have seen something that's like y plus ay prime equals a constant, something like that. That's all this differential equation is. It's one of the early ones in your differential equations class, and it's solved by using an integrating function.
I'm just assuming then by solving it that way that the shear tensor gamma dot is just a constant.
Right, but it doesn't have to be a constant. This can
It's
be,
a partial.
this can be, in fact, both of these can be a function of x. It's the same method. Okay, so the integrating function that we use for this is going to be 1 over lambda e to the t over lambda. And this, back when I studied differential equations, we were just told that it's the integral of this function with respect to the variable there. But since I'm not teaching differential equations, I don't feel the need to go into those details. The bottom line is I'm picking this function. This is an integrating function, and I'm going to multiply it through this differential equation. And magically, because I've correctly chosen the integrating function, the left-hand side is going to factor. By factor, I mean it's going to group to be some product that's just a derivative with respect to time. It's a very common technique. Again, I don't want to spend a lot of time on differential equations, so if you want to know the details, go check your notes in differential equations. But you can at least follow what I'm going to do here. I'll multiply this through. I get 1 over lambda e to the t over lambda times tau plus 1 over lambda times lambda is 1 e to the t over lambda partial tau dt equals minus eta naught gamma dot naught 1 over lambda e to the t over lambda. And I do have that. We're good. This is a tensor. I don't know how this became gamma dot naught somehow. This is the tensor gamma dot. Now, the integrating function method, that choice of integrating function is entirely for this next step. It's entirely for the fact that now the left-hand side is equal to d by dt of the product e to the t over lambda tau. Okay, let's see if that's right. Maybe I need a 1 over lambda. So let's check it. It's the first times the derivative of the second plus the second times the derivative of the first. So this term is this one. This term is that one, and it's correct. So this is what I meant by factoring. I multiply through by this integrating function, and the left-hand side becomes d by dt of a product now, of a combined group of variables, which is very nice. Because now I'll just be able to integrate that. Right-hand side stays the same. Minus eta naught over lambda, e to the t over lambda, gamma dot the tensor. So now this looks like d by dt of some function equals some grouping of variables. So that I can integrate. Now I'm going to integrate, and the question is over what limits should I integrate this? And because we're dealing with fluids with memory and the time dependence, I want to add up all the effects from infinitely far back into the past up to the present time. Okay, so I'm going to integrate this from minus infinity to the present time. So we can just sort of write that for starters. So this is d phi integrated from minus infinity to t equals the integral from minus infinity to t of minus eta naught over lambda. Now, here I have a problem. There's already a t here, and I don't want to get that variable t, which I'm integrating over. This is integrated over time. I don't want to get that variable confused with my limit. Too many t's, it's confusing. So we call this t prime, is the dummy variable of integration. So this is gamma dot at t prime. Integrated. So when I'm done with the integral, I will have evaluated and just t's will appear, and then it'll be equal to the time function on the left. All right, so the left-hand side just becomes phi, and phi is this stuff. So I get phi evaluated from minus infinity to t, and that's equal to e to the t prime over lambda tau of t prime evaluated from minus infinity to t. So this is the left side. And we can do this limit. At minus infinity, e to the minus infinity is 0. The stress at minus infinity is probably also 0, but it's certainly not infinite. So whatever it is, when I multiply it by minus infinity, I get 0. So I get 0 minus e to the t over lambda tau at the current time. Oh yeah, I was just checking my notes as to where that minus side went. So yeah, you're absolutely right. It's the upper minus the lower. Thank you. Because I was a little confused by that minus sign myself. Okay, and now the right-hand side just stays as it is. So let's summarize here. The left-hand side is e to the t over lambda. The stress at time t, which is what we were solving for in the first place, equals minus, I'm taking this minus sign out now, integral from minus infinity to t of eta naught over lambda, e to the t prime over lambda, gamma dot of t prime dt prime. Tensor. Thank you. And we're essentially done. Now, there is this e to the t over lambda on the left. Let me just move that to the right. E to the t over lambda, I can move to the right. I can put it in the front here as e to the minus t over lambda. Or I can move it inside. It doesn't matter because it's not a function of t prime. It's a function of t. So I'm going to move it inside. That's the usual way. And I get my final result. Tau of t equals minus the integral from minus infinity to t of eta naught over lambda e to the, and this is how it's usually written, t minus t prime over lambda gamma dot dt prime of t prime dt prime. So double check me. This is e to the minus t over lambda. That's that term. E to the plus t prime over lambda. That's that term. And this is the Maxwell model again. If you have a good memory, you'll know that we've seen that before. when I finished my adding up of various terms, I got this exact same result. So there it is. Tau equals minus the integral from minus infinity to t, a to naught over lambda, e to the minus t prime over lambda, gamma dot of t prime dt prime. Same equation. So they come from the same, well, the physics feels a little different, but it comes out to be exactly the same thing, so it must be the same physics. So incorporating an exponentially decreasing memory is the same as adding up viscous and elastic effects in series the way Maxwell did it. Now, maybe this doesn't seem that friendly to you because there's a big integral sign in it, but that's in our future. All constitutive equations from here on out are going to be either differential equations or integral equations. And in fact, when I started out in rheology in the early 80s, people divided themselves up into people who worked with integral equations and people who worked with differential equations. There was a big division because what math you use on them is a little bit different. And actually, there still is something of a divide in that sense nowadays, although a little bit less so. So we can't avoid either having our starting differential equation, which was a Maxwell model also, or an integral model. We can't get away from it because we need either integrals over all past times to tell us about memory, or we need time derivatives to tell us about the rate of change of things with time. We just can't live without them. Now let's get back to the problem at hand. Let's predict the steady shear material function for the Maxwell model. We have it explicit in stress now. Now we just have to plug in. Okay? So it's a little nasty, but there's only one place to put the gamma dot tensor. Okay, so we do that. We're going to predict viscosity, first normal stress coefficient, second normal stress coefficient for the Maxwell model. As we discussed a minute or two ago, if we're talking about viscosity, steady shear flow, we know gamma dot. It's 0. Gamma dot, the tensor has these two non-zero parts because it's steady shear flow. And we need to put this in here. Now remember, just think of this equation as 9 equations. So when we put 0 in there, we get that the stress is 0. When we put gamma dot naught, we get an integral with a constant in it, and we can do the integral. And so those are the only two things we ever have to put in there, either 0 or gamma dot naught. So for starters, psi 1 and psi 2 are still 0. Still our boring friend 0, because they're going to have to do with the components along the diagonal, and it's still multiplied by gamma dot, this tensor, and so they're going to be 0. And so we're just going to get the viscosity from this tau 2,1 position. All right, so let's put it in there. Tau at the current time t is equal to minus the integral from minus infinity to t of these constants, these variables, and then this tensor. The time dependence, this is evaluated at t prime, but at steady flow, it's a constant. It's the same at all times. When we go and do a startup, it gets trickier you know, because sometimes it's going and sometimes it's not. But this is the simplest case, the steady shear flow. And we get tau 1,1 equals tau 1,3 equals tau 2,2 equals tau 2,3 equals tau 1,3,1, 3,2, 3,3, 0. And tau 2,1 now is the only remaining equation, is minus. Now these are all constants. That's going to help us with our integral. Eta naught over lambda times gamma dot naught e to the minus t prime over lambda dt prime. So that's an integral of an exponential. So let me take those constants out front. That's my usual habit. The way I learned to do these integrals is, this is e to the u du. So if it's e to the u du, then the integral of that is e to the u. So if u is minus t prime over lambda, du dt prime, okay, I'm taking t prime derivative, is 1 over lambda dt prime. So I make this into du, but I can't just add a lambda. I have to take the lambda back out. So now it's e to the u du. And so the integral is e to the u. Tau 2,1 equals minus eta naught gamma dot naught e to the u evaluated between minus infinity and t. Please tell me if you find any algebra mistakes on my part. Because if we don't get the right answer, I have to come back and find them anyway. All right, so now we evaluate the limits, and we get minus eta naught gamma dot naught. At the upper limit, it's e to the t minus t is 0, so e to the 0 is 1, minus e to the t prime equals minus infinity, so this is infinity, but then there's a minus sign, so it's e to the minus infinity, it's 0. And now the definition of viscosity. Viscosity is minus tau 2,1 over gamma dot naught. That's right here, the definition of viscosity. We've calculated tau 2,1. It's minus eta naught gamma dot naught. Put that in. And the parameter eta naught in this constitutive equation is the viscosity for all values of gamma dot naught. Okay, so this model predicts constant viscosity. It didn't turn out that anything was a function of gamma dot naught, which is a bit of a disappointment because that's one of the things we know happens. We know that the viscosity does vary with shear rate. And we had high hopes for this model. We know that it has memory effects, but apparently memory effects alone aren't going to give us shear thinning. This model definitely has memory effects, but it's not sufficient to have memory. It turns out that you need nonlinearities to get shear thinning, and this is a linear model. It's a linear model in two ways. One, we just added viscous and elastic terms in the Maxwell approach. Or in my memory approach, I just kept adding what happened 1 second ago, 2 seconds ago, 3 seconds ago. I just added them up There's no nonlinearity there. If I'm just adding them up, it's all linear. And it's that linearity that makes the predictions come out so straightforwardly. So these are the predictions in steady shear of the Maxwell model. Either way, okay? You could think of doing the prediction with the differential equation the same way as we solved the whole thing. You could put in the tensor here and then solve the individual differential equations. They solve the same exact way. This is a little handier because it's already explicit in stress. It predicts a constant viscosity and 0 normal stress differences. If we put in the elongational viscosity, we get a constant elongational viscosity at 3 times the 0 shear. So it predicts Troughton's rule. So that's nice. How do you do that? Well, you just put in the elongational viscosity gamma dot here, and then put in the definitions of the elongational viscosity. Now, it may be a little, I don't know, discouraging to see that after all this work, we just got a Newtonian model, okay? It's not Newtonian. We're going to see, for instance, in the step strain experiment, and in startup, and in the small amplitude oscillatory shear that we don't predict the same as the Newtonian. So something having a constant viscosity doesn't mean it's Newtonian. And there are some materials that have a constant viscosity, but then have interesting non-Newtonian effects. Okay? Unfortunately, it also doesn't predict these because it doesn't predict this first normal stress coefficient. But for some aspects of these so-called Boger fluids, materials of constant viscosity, this model works very well. So now let's take it one step further and let's calculate the step strain. Now this is a little bit more involved, but the technique is the same. So let's review the technique. All right. This is, we have the kinematics right here whenever we do a prediction of a material function. So we have the velocity vector, so we have gamma dot. And what did we do last time? We started with the constitutive equation. We wrote the tensor, which in the case of the step shear strain will not be this one. It'll have a variable function here. Ooh, a tricky variable function. So that'll take some attention. And then we carried out the integration until we got the stress component we were looking for, and we plugged it into the material function. So we're going to do that again. I'll call this example 2. Calculate G of t, which is the step strain modulus. All right, so we know the velocity vector, and so we can calculate gamma dot the tensor. 0, sigma dot of t, 0, sigma dot of t, the rest zeros. And we have a crazy function, the step function, for sigma dot. And so we have to just follow the mathematical rules here. This is the limit as epsilon goes to 0 of a function that has 3 parts. It's 0 at time less than 0. It's gamma dot, which is a function of epsilon. Gamma dot, look at the bottom there, says that gamma dot is equal to gamma naught over epsilon. So we'll put that in there for t between 0 and epsilon, and then it's 0 again. Let me sketch that so that it rings home here. Sigma of t is 0 until you get to t equals 0. Then it's something between 0 and epsilon, and then it's 0 again. So it's a little pulse function. The limit is then taken as epsilon goes to 0, and this business of gamma dot and the step up here is equal to gamma dot naught. And the smaller this gets, the bigger this gets. Okay? And so as the limit happens of epsilon goes to 0, this goes to infinity. That's what this is saying. As epsilon goes to 0, the rate of change is going to infinity. So it's an impulse function. As fast as possible, we shear it and get to the final resting place, and then we stop. All right, so we have to plug this in to get our stress component. So we need our constitutive equation. Stress is equal to minus the integral from minus infinity to t of eta naught over lambda, e to the minus t prime over lambda, gamma dot of t prime dt prime. Now we put our function in here, 0, sigma dot, 0, sigma dot, 0, 0, 0. And this says evaluate it at t prime. So I'm going to evaluate it at t prime by plugging t prime in. So once again, all the coefficients are 0 except tau 2, 1 and tau 1, 2 that are equal. So we can drop the tensor notation and just talk about tau 2, 1, which is the one we need anyway. Tau 2, 1 is the one we need in order to be able to calculate g. Tau 2, 1 equals minus the integral from minus infinity to t, eta naught over lambda, e to the minus t prime over lambda, times sigma dot of t prime. Now this function is a function that has, if I plug in t prime here, everywhere, to evaluate it at t prime, it's 0 most of the time. So that's going to help us to simplify this integral. Right? So from minus infinity up to 0, what's sigma dot? 0, right? Because from, as long as t prime is less than 0, it's 0. And then from t to epsilon, it's something, right? And then from, this is epsilon, actually. There's a typo there. T greater than epsilon, it becomes 0 again. So we can break our integral up into 3 pieces. So let me move the minus sign to the left so I don't lose it. I can move the lambda and the eta naught to the left so I don't lose them either. And now I have 3 integrals. The integral from minus infinity to 0. The integral from 0 to epsilon. And the integral from epsilon to t. I can do that with any integral, always break it up into different regions. And it's this e to the minus t prime, but it's times sigma dot, which is 0. And it's e to the minus t prime, and it's times gamma naught over epsilon. And it's e to the minus t prime times 0. Okay? So For t less than 0, it's 0. For t greater than epsilon, it's 0. And only the middle term is going to stay. So let me write those in. I left them out so that wouldn't look too nasty. Minus tau 21 lambda over eta naught equals the integral from 0 to epsilon e to the minus t prime over lambda times this constant gamma naught times this epsilon that I'm going to take a limit dt prime. We're back to integrating exponentials again. Luckily, those are the easiest things on the planet to integrate. All right, so let me take all my constants out, again, just to keep myself organized here. Tau 21, lambda over eta naught, gamma naught, epsilon equals. Right? Nothing's a function of t prime. They can all come out. Integral from 0 to epsilon of e to the minus t prime over lambda dt prime. E to the u du is equal to e to the u. So if u is equal to minus t prime over lambda, then du must be equal to 1 over lambda dt prime. So once again, I put a 1 over lambda here. I put a lambda here. And my answer is lambda e to the u evaluated from 0 to epsilon. This lambda is going to cancel that one. So I get minus tau epsilon over eta naught gamma naught we're putting this in for t prime. I get e to the minus t minus epsilon over lambda minus e to the minus t over lambda. Any problems? You can factor out e to the minus t over lambda. Yep. So I could write this as e to the minus t over lambda times e to the epsilon over lambda minus 1. So the last thing we need to do is take the limit as epsilon goes to 0. So let's move things back where they belong. Tau 21 equals eta naught gamma naught negative times e to the minus t over lambda times e to the epsilon over lambda minus 1 over epsilon. Limit epsilon goes to 0. So as epsilon goes to 0, what does this go to?
0 over 0.
0 over 0, which means we need L'Hopital's rule. Okay, so L'Hopital's rule. L'Hopital's rule says that if you have the limit as x goes to 0 of f of x over g of x is equal to the limit as x goes to 0 of df dx over dg dx. So we need to take the derivative of the numerator and the denominator with respect to epsilon. All right, so tau equals minus eta naught gamma naught e to the minus t over lambda. That's the front stuff. Limit as epsilon goes to 0 of the derivative of the numerator with respect to epsilon is, right, 1 over lambda e to the epsilon over lambda. Derivative of the denominator is 1. What does that go to? 1 over lambda. As epsilon goes to 0, this becomes 1, and there's a 1 over lambda there. So I get eta naught gamma naught over lambda e to the minus t over lambda. So we're there. We now need to just plug in our tau 21 into our formula to get the modulus. This is called the relaxation modulus, G. In principle, it's a function of t and gamma naught. We'll see if it's a function of both. Minus tau 21 minus eta naught gamma naught over lambda e to the minus t over lambda over gamma naught. G of t gamma naught equals eta naught over lambda e to the minus t over lambda. So in fact, it's not a function of gamma naught. It shows no nonlinearities. Here's the solution. It's in the notes. Eta over lambda e to the minus t over lambda. Let's see what that looks like. It's an exponential decay. So it says, written in dimensionless form, that when you step up, the stress will step up to some value and then it will decline. If you plot that prediction on a log-log graph, it looks like this, the same exact curve. Now let's compare it to real data. There you go. So this is the step strain data for a polystyrene, a very concentrated polystyrene solution. And sure enough, it's independent of strain as long as your strains are small. And it does start from some value and decay. Okay? It's not perfect, but it's not too bad. The Newtonian prediction is that when you're moving, you get stress, and when you're not moving, you get no stress. The Newtonian prediction is 0. G of t is in the limit as this step happens really fast. All the stress is happening only during the fast stepping, and then as soon as you stop moving it, the stress goes to 0. That's not what's observed. What's observed is there is a decline, and this model, this FACO model that we just came up with reasonable ideas but without that much more, does a darn good job of predicting it. And this prediction, this ability to predict, tells us what these parameters, eta naught and lambda, have to be. And because we know them, we have a way of calculating the parameters that go with the constitutive equation. So the only parameters we needed to identify this constitutive equation were eta naught and lambda. If we have them, we've got the whole constitutive equation. So all we need to do is do one step strain experiment. We get the two parameters. Eta naught over lambda is equal to this plateau level right here. And lambda is equal to 1 over about the knee level of this function. So it's very easy to fit. Now maybe you're not so satisfied with that fit. You think, we can do a lot better. And so on Monday we'll do a lot better. Oh, I don't have it out, but let me just give you a quick peek at Monday. With a little bit of work on Monday, we're going to get it to fit. We're going to get it to fit dead on. So that's what we'll talk about on Monday. Okay? Have a good weekend.